Video 3, lifecycle.nsf and using the XPages Toolbox. My name is Tony McCuen. I'm a senior software engineer with IBM in Ireland. I'm an XPages runtime subject matter expert and work on research and development of the server, client and mobile runtime, customer enablement, proof of concept development and technical pre-sales. I'm also involved with areas of user experience, performance and scalability, and system architecture. I'm a co-creator of the Global XPages workshops, an OpenNTF contributor, and sit on the IBM One UI Web and Mobile Adoption Workgroup. Further to this, I have co-authored 2 publications on XPages, the Mastering XPages book and the XPages Portable Command Guide book. Currently, you are watching Video 3. Video 3 is an introduction to the lifecycle.nsf application and using the XPages Toolbox. Inside the zip file for the XPages Masterclass Video Series 1 OpenNTF project, you will find the lifecycle.nsf application. This is a testing harness demonstrating a variety of XPages Request Processing Lifecycle use cases, all within a self-contained XPages application. Firstly, it introduces execution of the lifecycle phases using an application and further goes to demonstrate a number of advanced use cases, all governed by the XPages Request Processing Lifecycle. It uses a phase listener class to capture key phase entry and exit points. This allows us to dynamically introspect any given XPages request and see the console output accordingly. Prerequisites to running the lifecycle.nsf application are 853 UP1 or some version of OpenNTF XPages extension library or greater. You must also have access to a Domino server console, or if not, then you can use your Notes client OSGI console. This is in order to analyze the console output that is emitted as you work with the lifecycle.nsf application. And if you're not familiar with launching your Notes client with an OSGI console, it's simply a matter of adding 2 command line parameters to the shortcut, as shown here. -r params in uppercase, space, -console in lowercase. So as you can see inside my Domino Designer workspace, I have already opened up the lifecycle.nsf application. I've also opened up the index page, as you can see here. This index page is already set as the default launch option for both web and Notes client. So on the index page, you've basically got a list of links which target all the other XPages within the application, as you can see here. So here you have the list of links. Each one of those corresponds with one of the XPages that we see over inside the XPages design element category. Secondly, if I just scroll down the page, you'll notice the fact that there is this debug mode checkbox and button also. So what we've got here, if I just click on the debug mode, you can see that the checked by default option that we have here has a computed value. So if we just double click on the computed value, you can see here that we are using expression language and we're tying that to the debug bin and the debug property available on that particular managed bin. Secondly then, if I take a look at the apply button that we see here, let's just look at it inside the source. Now, as you can see here, the button has an event handler which is submitting to the server side and executing some server-side JavaScript. Now, the important bit of code that we can see here is on line 143. Note the fact that I'm also setting debug mode then on the debug bin. So basically we use the checkbox to either turn on or off debug mode and then use the button to apply that debug mode setting against the backend debug bin. So before looking at the debug bin, let's take a deeper look at the application itself. I'm now just clicking on the Package Explorer to look inside the application. So let me just scroll down through my applications, and in the list I find the Lifecycle application. So inside the web content webinf directory, I'm taking a look at the facesconfig.xml file. Inside this facesconfig.xml file, we can see a number of different artifacts that are being registered with the XPages runtime. Firstly, we can see a lifecycle phase listener registering a debug bin phase listener class, and we'll come to look at that in a moment. We can also see the debug bin managed bin being registered, the one that we just referred to earlier. Interesting to note, you can see the managed property defined here with a default value of false. Now let's go and look at the two implementations for those two classes, the debug bin and the debug bin phase listener. If I expand out the code Java package structure, I can see a number of different packages listed here. And I'm interested in a couple here at the moment, the bins package and the lifecycle package. Here I can see the debug bin and also the debug bin phase listener. So I'm just going to open up both of those so that we can look at the implementations. Firstly, looking at the debug bin class. The debug bin is nothing more than a simple POJO used to manage the state of debug mode. That debug mode is represented by this debug Boolean member variable and managed by way of these getters and setters that we see available on the debug bin class. Secondly, looking at the debug bin phase listener class. As we can see here, the debug bin phase listener implements this Java Faces event phase listener interface. This special interface comes from the Java Server Faces API. If I just open my browser and do a search for the interface name, we can look at the Java Server Faces documentation, and here we can see the specification of the interface. And as described here, we can see that a phase listener is an interface implemented by objects that wish to be notified at the beginning and ending of processing for each standard phase of the request processing lifecycle. So in order to provide this functionality, this interface declares three methods for implementers. And as we can see here, there's an after phase method, a before phase, and a get phase ID. So if we now go back to Domino Designer and take a look at our debug bin phase listener class, we can see that it does implement the phase listener interface, and we can see those methods defined on the interface implemented here within the debug bin phase listener class. Firstly, we can see the method get phase ID implemented. In this case, it is using a special constant that allows this debug bin phase listener to listen for any of the phases. This constant could be changed to some of the other types, as you can see here. We could indeed implement this phase listener to be notified about execution of any of the 6 phases, as you can see here. But in this case, we're using the any phase option, so we capture notification about all phase executions. Next, we have the before phase method implemented, as you can see here, but also the after phase. And within the body of each method, you can see here that we are using our debug bin to establish if we are indeed in debug mode. And if we are, then we emit console output relative to the current phase that's being processed in the before phase and after phase methods. This provides us with a very convenient way of establishing when a phase begins and when a phase finishes. And what we can then do is put print statements within our other business logic, and so forth within the application, so that when you, for example, click on a button or follow a link and so forth, those print statements then get emitted within the appropriate phase within the lifecycle as it gets processed. Therefore, you've got a great way of introspecting the request dynamically as it happens. So those are some of the key artifacts within the application which allow us to then dynamically introspect requests posted against the application. Let's now take a look at the application itself. So I'll just open my browser and navigate to the lifecycle.nsf application. So as you can see here, the index page has been loaded. And when I scroll down here, you can see the debug mode checkbox. And if you follow any of the links within the index, you will find that a new tab will be opened within your browser that will then let you work with that particular test harness. Let me now just minimize my browser and bring up my server console. And now let's choose one of the sample pages within the application. So what I'm doing here is picking test process validations phase randomly from the selection within the index. And I click on the submit button. So here we can see I do have some validation failures, but there's nothing particularly interesting happening on the console, as we can see here. So let's go back to the application and go to our debug mode checkbox. I check the checkbox and click on apply. And immediately we can now see that there is console output telling me that we have turned on debug mode, as we can see here. And we're starting to see some interaction with the lifecycle for that particular request. Let's go back to our test process validations page. And if I click on submit once more, you can now see that we do indeed have console output, as we can see here, and letting us know when each of the phases begin and complete as we proceed through the processing of that particular request. So for example, in that case, we restored the view, applied request values, run process validations, which, as we can see within the application, has failed. And of course, that then means that the application fails over and executes the render response phase. Again, just let me fill in some of the values. So for example, let's put a couple of values into those offending fields and submit. And of course, in this instance, we can see that the validation succeeds, and we do indeed execute all 6 phases of the lifecycle: 1, 2, 3, 4, 5, and 6. And also worth noting is the fact that within that particular request, when I clicked on the submit button, there was a print statement in the event handler for the button, which was printing out the statement hello on the console, as you can see here. So again, an example of the event handler being invoked within the invoke application phase. So all in here, as you can see, this application contains a lot of different examples that demonstrate different aspects of interacting with the XPages Request Processing Lifecycle. And by turning on debug mode and using our console output, we can then analyze the information and try to gain an understanding of what's actually happening for any of those requests. In this second section of video 3, you will learn about using the XPages Toolbox effectively. The XPages Toolbox is an XPages based application that runs on top of the Domino server or indeed the Notes client. It is an NSF that needs to be installed on your Domino server or within your Notes client. And there are also a number of other steps that must be undertaken. There is a profiler jar file that needs to be added to the JVM launch properties, and you also need to update your Java policy file in order to give elevated security privileges to the NSF. And as a best practice, you should get into the habit of using the XPages Toolbox during your XPages development or testing cycles to periodically, or indeed per request, profile CPU, memory, and backend usage. You can, of course, also use it to control logging of the XPages runtime loggers, view current threads that are running in the HTTP process, or indeed create Java heat dumps or XML memory dumps, which can then be analyzed inside third-party tools. And it is important to note that it should only be used in a production server for problem resolution. This is because the XPages Toolbox collects and aggregates sensitive data taken from the server, but also from any of the user sessions and so forth. So ideally, if you do need to use it on a production server, just do so for that period of time until you resolve the problem and then remove the NSF from the server afterwards. It is available as a freely downloadable project from OpenNTF. Just do a search for XPages Toolbox, and there are full PDF instructions within the project download files that describe all of the steps above in terms of installing the profiler jar, JVM launch options, and so forth. As explained, you can use the XPages Toolbox to profile your XPages applications in terms of CPU, memory, and backend usage. Over and above that, the XPages Toolbox provides very deep profiling insight into your custom application code also, by way of using profile blocks. So for example, inside your server-side JavaScript code, you can declare special profile blocks using this type of notation, as we can see here, underscore underscore profile. And then you open up the parenthesis and define a mandatory first parameter and an optional second parameter. Basically, the first parameter is used as a block identifier. So when you profile the application and you look at the profile results, you can readily identify your own custom profile blocks based on the special block identifier that you've supplied for the first parameter. The second parameter is simply supplementary information that you might want to turn up inside the profile results. And we will be looking at worked examples of this in a few moments. So basically what you're doing here is wrapping your own custom server-side JavaScript code with these special profile blocks. And more than that, the profile blocks can also be nested within each other. So for example, you may have several levels of profile block information nested, such as inside nested for loops and while loops and so forth. And this means that your profile results will be much richer and much more meaningful in terms of the information that is collected by the profiler for any given profile run. Also, the same profiling engine can be used inside your custom Java or managed Bean code. In this case, instead of using profile blocks, we use a decorator pattern that enables profile blocks within your Java or managed Bean code. So for example, as we can see in this fragment that essentially describes the pattern, we can see that we have two methods, one a public method, one a private, and we also have a private static final variable. So first off, we have the private static member, which is the profiler type. We declare that and we specify our own arbitrary string identifier for that profiler type. So in this case, we can see it has been named my custom profiler. Secondly, we have a private member method. So as we can see here, it has been named with an underscore. Inside this method, I will have the real implementation of my code for my method. But what we're doing is using the decorator pattern to create a public version of the method. So in this case, we have our private underscore my method, but we then expose a public version of my method, as we can see here. This is the version of the method that will be used by any dependent code and is publicly accessible on the API of my custom object. And within this method, we then test for the profiler. So for example, we can see that there is an if statement here checking if the profiler is enabled. We then create a profiler aggregator object and start the profile block. The current time is captured inside the long start time variable, And we then have a try finally code block where you can see that the underscore my method variable is called. After that is executed, the profiler then ends the profile block, and in doing so captures all of the profile information that is required during that particular execution. If it's a case that the profiler is not enabled, so for example, if it's not turned on or if it is not installed on the actual client or server, this statement will drop into the else clause and still execute underscore my method. So by using this pattern, you can still create profile blocks inside your custom Java or managed bean code. And also these profile blocks can also be nested, just like inside your server-side JavaScript code. And again, all of the data that is captured during any profile run will also capture what comes from these custom Java managed bean profile blocks and aggregate that into the final results. So it is also worth noting that these profile blocks are non-invasive. When I say that they are non-invasive, what I mean is that you can leave these custom profile blocks inside your server-side or Java code, and they will have no impact on performance or scalability because they use very highly optimized back-end code. So there will also be no negative effect on your XPages applications or on your server or client, even if the XPages Toolbox is not installed. The profiling engine is part of the XPages runtime. So therefore, the XPages Toolbox is just a supplementary part of the whole equation, which allows you to use an application to visualize the profiling information. And the big upshot for you as the XPages developer is that because they are non-invasive, you can therefore leave your profiling blocks in place and they will support you during future profiling and maintenance tasks that you may need to carry out on your XPages applications. I'm now going to show you the XPages Toolbox and demonstrate how we use it to profile an application. I'm going to use the XPages Toolbox to profile one of the test harnesses within the lifecycle.nsf application. Firstly, just let me log into the application. And as you can see, when we log in, we are presented with a tabular interface. Each one of these tabs indicating its primary purpose, as you can see across the different tabs. For example, if we look at the CPU Profiler tab, we are able to use this tab to profile our application. This is where we can do our CPU and memory profiling. And after we capture profile information, we can then use the different views that we see here in the left side navigator to look at that profile information in different ways. Also, the Backend Profiler. We can use the Backend Profiler tab to profile backend classes. And after we do a backend profile, we are then presented with a list of profile results, which we can then drill down into to gain further insight into the backend class activity. The Runtime Monitoring tab allows us to take a snapshot of memory at any point in time, and from that we can see how many component modules or NSFs are loaded, how many sessions are within those applications, and how much JVM heap memory is being used. Under the Session Dumps tab, we can generate JVM heap dumps from here, but also XML memory dumps, and use that information inside third-party tools to analyze the JVM heap space usage. Under the Periodic Snapshots tab, we can use this to take periodic snapshots using the CPU Profiler. This can of course be very useful on a production server where you want to analyze information over a period of time, taking periodic snapshots automatically. Under the Threads tab, we can see a list of all running threads within the Domino server at this point in time. As a developer, what I can do is use this information to identify any given thread that I might be interested in and use that inside an Eclipse debugger to then debug into that particular thread. And finally, under the Logging tab, we can see here that we have a list of different loggers that have been registered with the XPages runtime. And what you can do here is use this interface to dynamically change the level of any given logger. So for the purposes of this demonstration, using the XPages Toolbox and the lifecycle.nsf application, what I'm going to do today is use the CPU profiler and the Backend Profiler. So as you can see here, there's a number of buttons on the CPU Profiler tab. We have the CPU Time Profiler and the Wall Time Profiler. And then we have other ways in which we can stop and reset the profiler and so forth. So what's interesting to note here is the difference between CPU time and wall time. And what we're going to do is use our lifecycle.nsf application to try to describe the differences between those two. Inside the lifecycle.nsf application, you will find one example test harness, the test CPU time versus wall time example. So I just click on it and open it up, and I'm just going to minimize my browser a little bit so that we can see the server console in the background. So as you can see here on the test CPU versus wall time XPage, there are 3 buttons. Each one executes some backend server-side logic. For the first 2 buttons that we see, that's the run CPU intensive task versus the run non-CPU intensive task. Let's take a look back inside Designer at what those are actually doing. So I'm just going to go back here to Domino Designer, and if we open up the test CPU versus wall time XPage and look at the source, what we can see here for the first button, we have a server-side event handler that is running server-side JavaScript. And it's basically using up CPU cycles. It executes a for loop for 10 seconds, and in doing so, it performs some long division, as we can see here. So obviously, it's going to use up the CPU. If we then take a look at the second example, run non-CPU intensive task, what we can see here is that, again, we have a server-side event handler. But in this case, the server-side JavaScript simply sleeps the system for 10 seconds. So this implies that it is not going to use any CPU. So let's now go back to our application and also have our Domino server console just sitting in the background. So first off, what I'm going to do is come back to the XPages Toolbox and start the CPU Time Profiler. So I've just clicked on the Start CPU Time Profiler button, and I'll come back to my application, and I'm clicking on the first of the 3 buttons. So right now my system is going off to execute that backend logic and use up the CPU. And at this point it has now finished. We can see here on the Domino server console that the operation started performing at 10:40:31 and finished at 10:40:41. So exactly 10 seconds have been used in that case. But let's look at our XPages Toolbox results. I come back into the profiler. Let me just increase the size of the browser, and I click on Stop Profiler. So immediately here I can see the results of the profile run. And let me just describe the data that we're looking at. So first off here we can see the timestamp of the particular profile run. When I expand the timestamp of the snapshot, I can see that there was 1 request made during that profile run. Because bear in mind, you could make several requests during any given profile run, and the data would be aggregated all together under that profile run. So in this particular example, there was 1 XPages request made, and if I expand out that request, I can now see the different lifecycle phases that were processed during that request. So in this case, there were 6 phases involved, so it's obviously a post type request. And under some of the phases, we can see that there is further activity. So I'm just going to expand everything at this point, and also increase the number of rows that we're looking at to 100. So notice the fact that we are looking at a view, and down the left side we have a view navigator, which allows us to toggle the view into different types of views. So for example, at the moment we're looking at the hierarchical all. If I change hierarchical all to hierarchical dominators, what it's doing is filtering out all of the entries that have a 0 time. So effectively all those entries or execution points that took no time are eliminated from the view, and we get a view showing us just those entries that did use up some CPU time. Other views we can look at, for example, by count. So here in the count column, this shows us the number of times that any given expression was computed. So for example, taking this first one that we see here in the view, this expression was executed 5 times during that request. Furthermore, if I click on the count column entry, I can see the details in drill down format, as you can see here. So I just hit the back button. That takes us back to our by count view. And then there's other views as well, by total time, by specific time, and by average time. Now let me just take a look at the by specific time entry. So again, this view is showing us the by specific time. As we can see here, the first column shows the specific time for any given expression, and it's sorted in descending order. So let me just go back now to the hierarchical all. It is important to note that these times are all in milliseconds. So where we can see here an entry showing us 9766, this is 9,766 milliseconds, or just short of 10 seconds. So in terms of the request that we've just made, let's now analyze the information. If I scroll down through the information, first off, what I can see is that the total time of the request was just shy of 10 seconds, as we can see here. And if we further scroll down through the view information, most of the entries have taken no time. It's only when we look at the invoke application and restore view phases information that we can see some degree of CPU usage. So what this profile information is telling me is that that particular request was held up doing something inside this particular expression at the very bottom. Here we can see this JavaScript expression, and it took in the order of just shy of 10 seconds. And looking at the very last column, here I can see, again, total time taken for that particular operation. Now, the important thing about the very last column is that it shows the specific time. So the specific time column is showing us the exact specific time for each of the operations that we see listed individually. And by looking at that, when I come down to the very last entry, what we can deduce from this is that for the invoke application JSF phase, when it was processed, it did take just shy of 10 seconds. But in the specific time column, we can see here that the invoke application phase itself didn't use any time. It was indeed this specific execution point which did take the exact amount of time. Furthermore, if I hover over the first column, here you can see that it is a link, and again I can drill down into that specific JavaScript expression. And here we can see in the drill down information the exact fragment of server-side JavaScript that we had been looking at earlier. The for loop that executes for 10 seconds doing long division. So once again, I'll just hit the back button. So we can see from this particular profile snapshot that this particular request did take just shy of 10 seconds. Now, moving on to our second example, Let me just come back up here and reset the profiler. It is important to reset the profiler in between snapshot requests in order to reset the timers and counters. And then just let me start the CPU profiler again. Once again, I'll minimize my browser so we can see our console output. And we'll now revisit our application. So let's just go ahead and click on the second button. So recall from earlier, this is the button that sleeps the system for 10 seconds. Sleeping the system implies that it uses no CPU. So let's now go back to our toolbox and stop our profiler. So once again, I'll just increase the number of rows that we're looking at to 100. And let me just collapse everything. So notice the fact now we have a new snapshot run. And it appears at the top of the list. So again, let's just look at the specifics of this snapshot. So first off, what we can see is that the total time now is 0. And if we scroll down through the information, we can see that everything appears to be 0. So what we're seeing here is the results of us profiling the CPU, but the system being slept for 10 seconds. So of course then, in terms of CPU time, nothing has been used, hence the 0 time that we are seeing. And if we took a look at the particular server-side JavaScript that was sleeping the system, we can see it listed here. And of course, if we drill down into the expression, we can see here that the system was being slept for 10 seconds. But of course, the total time is 0 and specific time 0. So those two examples that we've just looked at essentially demonstrate what CPU time profiling is. But let's now study wall time. Here we can see another option to start the wall timer. So once again, let's take our second button example. Once again, let me reset the profiler. And this time we will start the wall timer. Let's revisit our application. So once again, I'll click on our second button. And now that the request has finished, I will revisit the toolbox and stop the profiler. And now we can see that the same operation does indeed take just over 10 seconds. Again, if I scroll down through the profile information, we can come upon the JavaScript expression, as we see here, taking in the order of just over 10 seconds. The specific time being just over 10 seconds. And once again, let's just drill down into the expression. And again, even though we're sleeping the system for 10 seconds, we now have a wall time. We're observing the total time that it takes. Hence, we're getting specific time of just over 10 seconds. So essentially, this example is showing us what it means to profile wall time. If you can think of it essentially as watching the clock on the wall, and you're profiling using the wall timer, versus the CPU time profiler, where you're profiling time used within the CPU. And of course, the CPU may never be used in some cases, as we've seen with one of our examples. So let me now visit our last example. Let me reset the profiler. And in this case, I'm going to start the wall timer. And we come back to our application. And I'll just minimize the browser a little bit. And this time, I'm going to run the last button. So run some task. So here I click the button, and off it goes. So let's go back to our toolbox and stop the profiler. And once again, just let me expand the entries out to 100. And what we can see here immediately is that the request took over 23 seconds in this case. And if we scroll down through the information, we can see that most of the time is spent inside this execute backend logic method, as you can see here. What's also interesting to note here is the presence of these two identifiers, as we can see here. My code appearing in two entries, plus P1 and P2. Now, what's also interesting is if we drill down into this JavaScript expression, we can then see the exact expression that has been executed. And of course, we can use this backend side designer to look at the actual code itself. So just going back to designer, if I scroll down to our third button, here we can see the exact same server-side JavaScript expression. Now, what's interesting to note here is the presence of the profile blocks that were described earlier. So based on the profiling results that we have seen, all indications are that this backend util method is taking 23 seconds. So within this backend util class, we can see usage made of the profiling block decorator pattern. Here we can see our profiler type being declared for backend util profiler, and we have a private method called underscore execute backend logic. Further down, we can see the public version of the method without the underscore, so execute backend logic. This is the method that is being executed back in our server-side JavaScript. And of course, given that we have the profiler enabled and turned on, we do end up executing line 57 of this code. So let's now try to understand what might be taking just over 23 seconds to execute. So inside this backend util method, here we can see that it gets the current database and immediately then starts to run a for loop to create a number of documents and save those documents into the current database, and then get a view and subsequently get the view entry count before removing all the entries. And then on line 42, we can also see that it gets a database agent and invokes that agent here on line 44. So essentially, all of this code appears to be making use of domino backend Java classes. So when we look at our profiling results, we can indeed see that all of the XPages code involved in this request has taken zero amount of time to execute. The real problem lies within that backend util execute backend logic method. So this is one candidate whereby we could use the backend profiler to try to gain further insight into what's taking that amount of time. So let me now click on the backend profiler tab, and in this case I'm going to start the backend profiler, and we then go back to our application. And again I just run some task, and now that that operation has finished, let's go back to our toolbox and stop our backend profiler. So in this instance, we can see that we now have an entry listed within the backend profiling results. And using the first column here, what I can do is click on the timestamp entry, which allows me then to drill down into the backend profiling information. And in this particular case, we can see then that the 23 seconds has been spent mostly inside the backend, as we can see here. Here we have a breakdown of the backend methods that have been executed. So using this backend profile, we can then see the wall times of those backend calls listed within this table. And the biggest offender that we can see in the table is indeed the agent.run code. As we can see here, agent.run took in the order of just over 15 seconds of the total time. So again, let's just go back to Designer. And now let's just open up the My Backend agent that we see listed here. So as we can see here, the agent does nothing more than simply sleep the system for 15 seconds, which of course is in line with the profiling results that we see back inside our XPages toolbox. So in summary, you can see how the XPages toolbox is a very powerful utility that not only lets you profile backend Domino Java classes, but also lets you profile the CPU usage in terms of how much is being used within the CPU itself versus the complete wall time that any given request might take. So all in, it's a very, very useful and beneficial tool to use and get into the habit of during your XPages development and testing cycles. During my description of the XPages toolbox, I had shown you the Session Dumps tab. Under that tab, I had mentioned the fact that you can generate JVM heap dumps or XML memory heap dumps and then analyze those in third-party tools. Well, in this closing section of this third video from Series 1, I just want to give a quick demonstration of using the XPages toolbox to generate a heap dump and to then use a third-party tool to analyze that heap dump, but to also give you some supplementary information in the area of creating heap dumps and analyzing those. So the XPages toolbox can be used to generate a heap dump of the JVM running within the current HTTP task. There is a button under the Session Dumps tab which allows you to generate a JVM heap dump. There are also two other buttons that can be used to generate XML memory dumps. And as of Domino 853, there are new commands available on the Domino console: tell HTTP XSP heap dump or Java dump, both of which will trigger corresponding heap dump and Java dump files. Once you have generated a heap dump, either by using the XPages toolbox or from the Domino console commands, or indeed if the system generates the heap dump automatically, you can then analyze the information within the non-human readable heap dump file using a third-party tool such as the Eclipse Memory Analyzer. This is a free download available from eclipse.org, and in order to be compatible with the heap dump format generated by the Domino server, you also need to install this IBM Diagnostic Tool Framework for Java extension. Again, a freely downloadable extension from DeveloperWorks. And just one last point I want to make as well is that even though you can manually create the heap dumps, the Domino server will also generate them automatically in production when some failure occurs. For example, when the XPages runtime runs out of memory, there will be an out-of-memory error raised, which will subsequently cause the creation of a heap dump automatically. You can then use that heap dump to try and identify the cause of the out-of-memory situation and try to resolve that back inside your application then. Under the Session Dumps tab within the XPages toolbox, you have buttons here which allow you to do different things. This first button allows you to generate a JVM heap dump versus these two buttons which allow you to create XML memory dumps. And the two are quite different. Firstly, if I click on Create Part XML Session Dump, the runtime generates a partial memory dump using XML format and places a link here within the view, which allows me then to open that XML file in a new tab. And here I see information from that partial memory dump. Versus if I were to generate a full session dump, so here I've clicked the button again for full session, I can see now that the file size is much larger. And what we're getting is a more detailed introspection of the memory dump using XML. So if we then choose to open that in a new tab, here we can see a much more extensive breakdown of information. And we can read these XML files in order to deduce how we're using memory in terms of user sessions, component tree, objects, and so forth. And bear in mind, these generated XML files will contain sensitive information drawn from the current applications and from the server itself. So let me just close that. And if we come back then to the Generate JVM Heap Dump button, that's the first option. Let me just reduce the size of the browser slightly. And in this case, what I'll do is click on the button, and it goes off and generates a heap dump. And in the Windows Explorer that I have opened down below, we can just see that new heap dump that we have just created. Unlike the XML memory dumps, this file is not human readable. So for example, if I were to try and open this in Notepad or similar, you can see that it is a non-human readable file. So that's where your third-party tools come into play, whereby you can analyze the information within that portable heap dump file. And also, as described earlier, if we take the Domino Server console, and let me just bring it up here, and if I now issue one of the new HTTP XSP commands to generate a heap dump, we can see the same type of operation being carried out in that our Domino server goes off and creates the new heap dump file in the background, as you can see here. And finally, let's do one other thing. Let's force the system into creating a heap dump file. If I come back here to Domino Designer, inside the second of the two applications, inside the XPages Masterclass Video Series OpenNTF project, you will find the perf.options.nsf application. Inside Designer here, I have already opened up the application. And if I open up the test out of memory XPage, as we can see here, it contains two nested repeats, both of which have a value of integer.maxValue. And as they iterate, they are creating controls explicitly inside the component tree for this XPage. As we can see here, we have repeat controls equals true for each of those repeats. And for the children of the nested repeat, we can see that it iterates and creates table rows with table cells and computed fields. So the important thing to note here is that what we're doing is forcing the system to create an out-of-memory error. So let's now just come back to our browser, and I've already opened up the application, as we can see here, but also let me just put the Domino Server console down below. And what I'll also do here is bring up the task manager, and we will look at the HTTP process. So I just look here at the performance graph for the NHTTP process, and I will just go ahead here now and click on test out of memory. And whilst we're waiting for that, I will also bring up my Domino server in the background. And whilst we're waiting here, what we can see is the fact that the CPU is now starting to spike as the repeats are being created and they iterate over their children. And the memory consumption is also increasing. And eventually what we will see is that the system fails over, essentially because the HTTP process runs out of JVM memory heap space. Subsequently, as we now see, that has created a heap dump within our Windows Explorer. We can see here that in the root of my Domino server, we do indeed have 2 new heap dumps created. And of course, back inside the browser, the server has responded to let the end user know that it cannot handle that particular request. So what is interesting now is to use a third-party tool, such as the Eclipse Memory Analyzer, to now analyze those generated heap dumps. So if I just open up my Eclipse Memory Analyzer, and now proceed to open up one of the generated heap dumps that we have just seen. So here we can see the 2 latest versions. So what I'll do is open up the first of the 2. And the Eclipse Memory Analyzer now analyzes the file and gives us back some useful information that we can then drill down upon to try to identify the out-of-memory error that was raised. Now that the Eclipse Memory Analyzer has finished reading the portable heap dump, we then get a report which is telling us about possible leaks within the system or problematic users of the JVM memory heap space. So for example, in this first case, we can see here that there was 184 meg of memory used from the JVM heap space by problem suspect 1. And problem suspect 1 is indeed a repeat control. So that is already telling us something about the most heavily used object within the JVM heap space. If I now look at the overview page, I can also mouse over the pie chart that we see here, and I can see details for any of the specific objects collected within that pie chart. And in the case of our repeat, what I'm going to do here is select the Show Retained Set option. And in this case, we get a drill down of all the objects contained within that repeat control. So essentially, these are all the objects that consume memory that are direct children of the repeat control. And from this information, I can already start to identify some of the controls that have been used back inside the XSP markup. So for example, we have our table cells, as we can see here, and our computed fields turning up inside the memory output. So as you can see here, there's over 145,000 instances of each of these. And we can also see exactly how much memory is being used in this particular case. And as an XPages developer, I can now use this information to my benefit in order to allow me to optimize that particular XPage so that it won't use as much memory or create as many controls and so forth, in order to avoid any future out-of-memory error being raised within the system. Thank you. This is the end of video 3 from the first series.